Now that we know the definition of continuity, what it means to be continuous, we'll look at some examples evaluating different functions to see if they're continuous or the opposite of that, not continuous. That would be called discontinuous here. Okay, so the three functions we're going to look at are similar, related to one another, and we're going to look at the same point on each of these functions. For each one, we're just going to focus on what's going on at x equals 3. So from our definition here, our c value that we care about is going to be 3. Okay. So the first function, you can write it with me, f of x is going to be x squared minus 9 over x minus 3. Okay. And so to evaluate whether this is continuous or discontinuous at x equals 3, we're just going to tick right through our three criteria because these three things have all got to be true in order for our function to be continuous. Okay, so first off, let's check out f of c, our first criteria here, criterion, singular. All right, so f of 3, well, that's a little bit of a problem because if x equals 3, this denominator is going to be 0, and so the function is undefined at x equals 3. So f of 3 does not exist, and so we've failed the very first of our three criteria. F of c must exist for us to have continuity. Here, f of 3 doesn't exist, so as soon as you fail one of these three things, the function is discontinuous. Okay, f of 3 does not exist, so f of x is discontinuous. All right, discontinuous. Okay, now for our next function, it will be similar. Okay, but now it's going to be a piecewise function. So set yourself up some piecewise. And one piece will look like our previous function, x squared minus 9 over x minus 3. And this is true if x does not equal 3. Okay. And then our other part of the piecewise is that f of x equals 7 if x does equal 3. Okay, so now we've got a little more to investigate here. Let's see what's going on. Okay, first things first, we'll start out in the same place. Let's investigate f of c. So f of 3 here, okay, that's when x actually equals 3, and so that means we use this part of the piecewise function, and so our f of x value, f of 3, is going to equal 7. Okay, so yeah, f of c exists here. Exists, yay, check. Okay, so we need to move on to looking at the limit as x approaches 3 of f of x here. Okay. So our limit as x approaches 3 of f of x. All right, now remember the idea of approaching. As x approaches 3, that means our x values are getting very, very close to 3, but we don't actually care what's going on at x equals 3 itself for the limit, all right? So the limit is found in the approach, not at the actual point. So we can use the first part of our piecewise function, since we're looking at values approaching 3, but not necessarily equal to 3. Okay, so this means we could write the limit as x approaches 3 of x squared minus 9 over x minus 3. Okay, putting in the appropriate part of the piecewise function. And we saw how to evaluate something like that a couple sections ago. I believe in 2.2, we learned our tricks for evaluating limits algebraically. And this particular limit is going to fit very nicely into the idea of factor and cancel. So we have our limit as x approaches 3, factor that numerator. It's a difference of squares. And cancel out the x minus 3 factor. Okay. So would have the limit as x approaches 3 of x plus 3 is all that's left there. And then we can use direct substitution, the best trick of all. Plug in x equals 3 and then we get 6. Okay. So our limit as x approaches 3 of f of x equals 6. And f of 3 equals 7. So here we have met our first two criteria. Okay, f of 3 is 7, it exists. The limit as x approaches 3 of f of x also exists, it equals 6. But we've failed our third of the 3 criteria because the two numbers are not the same. So we have to say that this function is also discontinuous. So let's see. So f of x here is discontinuous also because f of 3 did not equal the limit as x approaches 3 of f of x. Okay, so also discontinuous there, just for a different reason now. Okay, let me separate some space on our page here so we can look at our third function. Okay. And our third function is also going to look similar to the first two. F of x, it's also a piecewise one. It's x squared minus 9 over x minus 3 if x does not equal 3. And it's going to be 6 if x does equal 3. Okay, so now you can probably see where we're going with this one. Here, checking our function value when x actually equals 3, spot on. F of 3 is 6, so the function value exists. The limit is still the same because limit, we're looking at the approach. X is approaching 3. Limit x approaches 3 of f of x, and it follows the exact same tricks as part B. So we get the exact same limit here. The limit is 6. And so then we can see that the two values are equal. And so now we've met all 3 criteria. So f of x here is continuous at x equals 3 because f of 3 equals our limit as x approaches 3 of f of x. Both of those equal 6. Okay, squeezed it in there. Good. All right, so we had discontinuous for the first one because our function value didn't exist. We had discontinuous for the second one, even though both pieces existed, they weren't equal. And so then in the third function, it was continuous because finally the function value and the limit equaled one another. So one thing to wrap this problem up here is to look at that function, x squared minus 9 over x minus 3. All right, because we've actually looked at this function in a previous section, if you'll recall. This this function, the not piecewise one, this really just looks like a line with a hole in it. Okay. So it looks like the line x plus 3 because of the way the limit shakes out. All right. So our function graph for this would just look like 1, 2, 3, 1, 2, 3, 5, 6. All right, our function graph would look like this: intercept of 3, slope of 1. And our first function, there is a hole right there. Okay. So that's what this function looks like, hole in the graph. Boop. On the second function, we have basically that same idea. It's still going to be a line. Okay, there's 3. Okay. So we've got our line, x plus 3 essentially. That's giving us the limit. Limit is approaching 6 there. Okay. But then because of this second part of the piecewise function, we have a point at 3, 7. So right here. Okay, so there's a limit and there's a point, but they don't come to the same value. All right. And then in the last function, we resolve that little issue there. There's 3. 1, 2, 3, 4, 5, 6. Okay, we still have the same basic line set up. But now, instead of having a hole right here, okay, there would be a hole from the first part of the piecewise function, but this second part of the piecewise function fills the hole right in because it tells us that we want f of 3 to equal 6. So that fills in that hole, leaving us with a nice continuous function. Okay, so it turns out that this discontinuity, the place where these first two functions are discontinuous at x equals 3, that discontinuity is going to be something called a removable discontinuity, because we can take out that discontinuous bit if we properly define where f of 3 should be. We can like fill in that hole and remove the discontinuous part. So there's going to be different types of these discontinuities, and we're going to look at those in the next video.